From worldwideweb.++.com/doc/tutorial/. Part 07. Learn by listening exercise. Functions. Functions allow us to structure programs in conveniently named segments of code to perform individual tasks. In C++, a function is a group of statements that is given a name, and which can be called from arbitrary locations of the program's source code. Functions typically operate on input data and generate output data. Within a function, statements can access input data using either of two techniques. Function input technique 1 of 2, the data can be passed into the function from the prior function or logic, using a memory dash, resident dash, stack, or function input technique 2 of 2, the function can access previously defined global data by name. Within a function, statements can generate or manipulate output data using either of two techniques. Function output technique 1 of 2, the data can be passed out of the function within a single parameter that is transmitted back to the prior function or logic, using a memory dash, resident stack, or function output technique 2 of 2, the function can manipulate previously defined global data by name. At the beginning of every function definition, all of the name and function input and output details are specified so that the compiler can allocate appropriate memory for its use and can anticipate its correct execution in the inputs and outputs it will need or may generate. The most common syntax to define a function is type name, open parenthesis, parameter 1, parameter 2, point, close parenthesis, open curly brace, statements, close curly brace. Where double quote, type double quote, is the type of the value returned by the function, open parenthesis, for example, double quote, int double quote, or double quote, void double quote, close parenthesis. Note that it is commonplace for functions to return pointers as parameters so that large amounts of data can be returned efficiently. Double quote, name double quote, is the identifier by which the function can be called. Open parenthesis, for example, double quote, initialize double quote, close parenthesis. Double quote, parameters double quote, open parenthesis, as many, as needed, close parenthesis, represent input cat. A list of parameters needed, as input to the function is contained within a pair of parentheses immediately after the name. Within the parenthesis, each parameter consists of two components. Parameter component 1 of 2, a type, open parenthesis, such as double quote, int double quote, or double quote, char double quote, close parenthesis, designating the size and meaning of the corresponding parameter in memory, and parameter component 2 of 2, an identifier, open parenthesis, such as double quote, counter 1 double quote, close parenthesis, serving as the name through which the corresponding parameter can be referenced. If the function needs multiple input parameters, they are separated from one another by a comma. Each parameter looks very much like a regular variable declaration, open parenthesis, for example, index, close parenthesis, comma, and in fact acts within the function as a regular variable which is local to the function. The purpose of parameters is to allow passing arguments to the function from the location from which it is invoked. After the parenthesis containing the input parameters, one or more double quote statements double quote form the function's body. These statements are generally formatted into a sequence or block, contained within a pair of curly braces. These statements specify what the function actually does. Let us have a look at a 17-line example. Line 01 of 17 / function example. Line 02 of 17, $, include left angle bracket, iostream right angle bracket. Line 03 of 17, using namespace std semicolon. Line 04 of 17. Line 05 of 17, in addition, open parenthesis, int a, int b. Line 06 of 17, open curly brace. Line 07 of 17, in r, semicolon. Line 08 of 17, r equals a plus b, semicolon. Line 09 of 17, return r, semicolon. Line 10 of 17, close curly brace. Line 11 of 17. Line 12 of 17, int main, open parenthesis, close parenthesis. Line 13 of 17, open curly brace. Line 14 of 17, int z, semicolon. Line 15 of 17, z equals addition, open parenthesis, 5, 3, close parenthesis, semicolon. Line 16 of 17, C out, double left arrow, double quote, the result is double quote, double left arrow, z, semicolon. Line 17 of 17, close curly brace. When this program is executed, it generates the following output. The result is 8. As you can see from a simple examination of the source code above, this program is divided into functions, addition, and main. Remember that no matter the order in which they are defined, a C++ program always starts by calling main. In fact, main is the only function called automatically, and the code in any other function is only executed if its function is called from main, directly or indirectly, close parenthesis. In the example above, main begins by declaring the variable z of type int, and right after that, it performs the first function call. It calls addition. The call to a function follows a structure very similar to its declaration. In the example above, the call to addition can be compared to its definition just a few lines earlier. The parameters in the function declaration have a clear correspondence to the arguments passed in the function call. The call passes two values, 5 and 3, to the function, These correspond to the parameters a and b, declared for function addition. At the point at which the function is called from within main, the control is passed to function addition. Here, execution of main is stopped, and will only continue after the addition function ends. At the moment of the function call, the value of both arguments, 5 and 3, are copied to the local variables int a and int b within the function. Then, inside addition, another local variable is declared, in r, and by means of the expression r equals a plus b, the result of a plus b is assigned to r, which, for this case, where a is 5 and b is 3, means that 8 is assigned to r. The final statement within the function, return r, ends function addition, and returns the control back to the point where the function was called, in this case, to function main. At this precise moment, the program resumes its course on main, returning exactly at the same point at which it was interrupted by the call to addition. But additionally, because addition has a return type, the call is evaluated as having a value, and this value is the value specified in the return statement that ended addition. In this particular case, the value of the local variable r, which at the moment of the return statement had a value of 8. Therefore, the call to addition is an expression with the value returned by the function, and in this case, that value, 8, is assigned to z. It is as if the entire function call, addition, 5, 3, was replaced by the value it returns, that is, 8, Then main simply prints this value by calling cout, the result is z, A function can actually be called multiple times within a program, and its argument is naturally not limited just to literals, as shown in this 21-line example : line 01 of 21 / function example. Line 02 of 21, $, include left angle bracket, IOStream right angle bracket. Line 03 of 21, using namespace std, Line 04 of 21. Line 05 of 21, in subtraction, int a, int b, Line 06 of 21, open curly brace. Line 07 of 21, in r, Line 08 of 21, r equals a dash, b, Line 09 of 21, return r, Line 10 of 21, close curly brace. Line 11 of 21. Line 12 of 21, int main, close parenthesis. Line 13 of 21, open curly brace. Line 14 of 21, int x equals 5, y equals 3, z, Line 15 of 21, z equals subtraction, open parenthesis, 7, 2, close parenthesis, Line 16 of 21, cout, double left arrow, the first result is double left arrow, z, double left arrow, new line, Line 17 of 21, cout, double left arrow, the second result is double left arrow, subtraction, open parenthesis, 7, 2, close parenthesis, double left arrow, new line, Line 18 of 21, cout, double left arrow, double quote, the third result is double quote, double left arrow, subtraction, open parenthesis, x, comma, y, close parenthesis, double left arrow, single quote, new line, single quote, semicolon. Line 19 of 21, z equals 4 plus subtraction, open parenthesis, x, comma, y, close parenthesis, semicolon. Line 20 of 21, cout, double left arrow, double quote, the fourth result is double quote, double left arrow, z, double left arrow, single quote, new line, single quote, semicolon. Line 21 of 21, close curly brace. Running this program results in the following output. The first result is 5. The second result is 5. The third result is 2. The fourth result is 6. Similar to the addition function in the previous example, this example defines a subtraction function that simply returns the difference between its two parameters. This time, main calls this function several times, passing in different parameters each time, demonstrating more possible ways in which a function can be called. Let's examine each of these calls, bearing in mind that each function call is itself an expression that is evaluated as the value it returns. Again, you can think of it as if the function call was itself replaced by the return value comma, as shown in these two lines colon. Line 0, 1 of 0 to z equals subtraction, open parenthesis, 7, 2, close parenthesis, semicolon. Line 0, 2 of 0 to cout, double left arrow, double quote, the first result is double quote, double left arrow, z, semicolon. If we replace the function call by the value it returns, open parenthesis, that is, 5, close parenthesis, comma, we would have line 0, 1 of 0 to z equals 5, semicolon. Line 0, 2 of 0 to cout, double left arrow, double quote, the first result is double quote, double left arrow, z, semicolon. With the same procedure, we could interpret cout, double left arrow, double quote, the second result is double quote, double left arrow, subtraction, open parenthesis, 7, 2, close parenthesis, semicolon. As cout, double left arrow, double quote, the second result is double quote, double left arrow, 5, semicolon. Since 5 is the value returned by subtraction, open parenthesis, 7, 2, close parenthesis. In the case of cout, double left arrow, double quote, the third result is double quote, double left arrow, subtraction, open parenthesis, x, y, close parenthesis, semicolon. The arguments passed to subtraction are variables instead of literals. That is also valid, and works fine. The function is called with the values x and y at the moment of the call, 5 and 3 respectively, returning 2, as result. The fourth call is again similar. Z equals 4 plus subtraction, open parenthesis, x, y, close parenthesis, semicolon. The only addition being that now the function call is also an operand of an addition operation. Again, the result is the same as if the function call was replaced by its result, 6. Note that thanks to the commutative property of additions, the above can also be written as z equals subtraction, open parenthesis, x, y, close parenthesis, plus 4, semicolon. With exactly the same result. Note also that the semicolon does not necessarily go after the function call, but, as always, at the end of the whole statement. Again, the logic behind may be easily seen again by replacing the function calls by their return value, as shown here colon. Line 0, 1 of 0 to z equals 4 plus 2, semicolon, slash, same as z equals 4 plus subtraction, open parenthesis, x, y, close parenthesis, semicolon. Line 0, 2 of 0 to z equals 2 plus 4, semicolon, slash, same as z equals subtraction, open parenthesis, x, y, close parenthesis, plus 4, semicolon. Functions with no type. The use of double quote, void double quote. The syntax shown above for functions. Type name, open parenthesis, argument 1, argument 2, point, close parenthesis, open curly brace, statements, close curly brace. Requires the declaration to begin with a type. This is the type of the value returned by the function. But sometimes a function does not need to return a value. In this case, the type to be used is double quote, void double quote, comma, which is a special keyword representing the absence of value. In this 14- line example, a function that simply prints a message may not need to return any value. Line 0, 1 of 13 / void function example. Line 02 of 14, pound sign, include left angle bracket, iostream right angle bracket. Line 03 of 14, using namespace std semicolon. Line 04 of 14. Line 05 of 14, void print message, open parenthesis, close parenthesis. Line 06 of 14, open curly brace. Line 07 of 14, see out, double left arrow, double quote, I may function. Double quote, semicolon. Line 08 of 14, close curly brace. Line 09 of 14. Line 10 of 14, int main, open parenthesis, close parenthesis. Line 11 of 14, open curly brace. Line 12 of 14, print message, open parenthesis, close parenthesis, semicolon. Line 13 of 14, close curly brace. When this code is executed, the following output is generated. I may function. Sometimes, a function requires no input data. Accordingly, when such a function is declared, the special keyword double quote, void double quote, can also be used in the function's parameter list to explicitly specify that the function takes no actual parameters when called. For example, print message could have been declared, as shown in this 4- line snippet colon. Line 01 of 04, void print message, open parenthesis, void, close parenthesis. Line 02 of 04, open curly brace. Line 03 of 04, see out, double left arrow, double quote, I may function. Double quote, semicolon. Line 04 of 04, close curly brace. In C++, an empty parameter list can be used instead of void with the same meaning, but the use of void in the argument list was popularized by the C language, where this is a requirement. Something that in no case is optional are the parentheses that follow the function name, neither in its declaration nor when calling it. And even when the function takes no parameters, at least an empty pair of parentheses must always be appended to the function name. See how print message was called in an earlier example. Print message, open parenthesis, close parenthesis, semicolon. The parentheses are what differentiate functions from other kinds of declarations or statements. The following would not call the function. Print message, semicolon. The return value of main. You may have noticed that the return type of main isn't, but most examples in this and earlier chapters did not actually return any value from main. Well, there is a catch. If the execution of main ends normally without encountering a return statement, the compiler assumes the function ends with an implicit return statement. Return 0, semicolon. Note that this only applies to function main for historical reasons. All other functions with a return type must end with a proper return statement that includes a return value, even if this is never used. When main returns 0, open parenthesis, either implicitly or explicitly, close parenthesis, comma, it is interpreted by the environment as that the program ended successfully. Other values may be returned by main, and some environments give access to that value to the caller in some way, although this behavior is not required nor necessarily portable between platforms. The values for main that are guaranteed to be interpreted in the same way on all platforms are 0. The program was successful. Exit_success. The program was successful, open parenthesis, same as above, close parenthesis. Open parenthesis, this value is defined in header left angle bracket, CSTDLIB right angle bracket, close parenthesis. Exit_failure. The program failed. Open parenthesis, this value is defined in header left angle bracket, CSTDLIB right angle bracket, close parenthesis. Because the implicit return 0, semicolon, statement, for main is a tricky exception, some authors consider it good practice to explicitly write the statement. Arguments passed by valuing by reference. In the functions seen earlier, arguments have always been passed by value. This means that, when calling a function, what is passed to the function are the values of these arguments at the moment of the call, which are copied into the variables represented by the function parameters. For example, consider these two lines colon. Line 01 of 02 int x equals 5, y equals 3, z, semicolon. Line 02 of 02 z equals addition, open parenthesis, x, y, close parenthesis, semicolon. In this case, function double quote, addition double quote, is passed 5 and 3, which are copies of the values of x and y, respectively. These values, open parenthesis, 5 and 3, close parenthesis, are used to initialize the variables set as parameters in the function's definition, but any modification of these variables within the function has no effect on the values of the variables x and y outside it, because x and y were themselves not passed to the function on the call, but only copies of their values at that moment. In certain cases, though, it may be useful to access an external variable from within a function. To do that, arguments can be passed by pointer reference, instead of by value. For example, the function double values in this 18-line sample doubles the value of its 3 arguments, causing the variables used as arguments to actually be modified by the call. Line 01 of 18 / passing parameters by reference. Line 02 of 18, $, include left angle bracket, IOStream right angle bracket. Line 03 of 18, using namespace std, semicolon. Line 04 of 18. Line 05 of 18, void double values, open parenthesis, in $a, comma, in $a, comma, in $c, close parenthesis. Line 06 of 18, open curly brace. Line 07 of 18, a asterisk equals to, semicolon. Line 08 of 18, b asterisk equals to, semicolon. Line 09 of 18, c asterisk equals to, semicolon. Line 10 of 18, close curly brace. Line 11 of 18. Line 12 of 18, int main, open parenthesis, close parenthesis. Line 14 of 18, open curly brace. Line 14 of 18, int x equals 1, y equals 3, z equals 7, semicolon. Line 15 of 18, double values, open parenthesis, x, y, z, close parenthesis, semicolon. Line 16 of 18, see out, double left arrow, double quote x equals double left arrow, x, double left arrow, double quote, y equals double left arrow, y, double left arrow, double quote, z equals double left arrow, z, semicolon. Line 17 of 18, return 0, semicolon. Line 18 of 18, close curly brace. When this code is executed, the following output is generated. X equals 2, y equals 6, z equals 14. To gain access to its arguments, the function double values declares its parameters as address pointers of the appropriate type for access to the corresponding variable in memory. In C++, address references are indicated with an ampersand following the parameter type, as in the parameters taken by double values in the example above. By the time the compiler gets into our main function and sees the first statement invoking our double values left parenthesis right parenthesis function, it already knows that 3 address pointers are expected, so it automatically passes the addresses of variables x y and z . When a variable is passed in this way, what is passed is no longer a copy. Instead, the function interprets it as a pointer to the variable itself, wherever it may reside in memory. This makes the variable identified by the function parameter directly available to the function, and any modification of their values within the function are reflected in the actual memory resident variables, wherever they may be stored. In fact, a, b, and c become aliases of the arguments passed on the function call, open parenthesis, x, y, and z, close parenthesis, and any change on a within the function is actually modifying variable x outside the function. Any change on b modifies y, and any change on c modifies z. That is why when, in the example, function double values modifies the values of its local variables a, b, and c, the values of x, y, and z, outside the function itself, are affected. If instead of defining double values as void double values, open parenthesis, in ampersand, a, in ampersand, b, in ampersand, c, close parenthesis, was it to be defined without the ampersand signs, as void double values, open parenthesis, in a, int b, in c, close parenthesis. Then the 3 variables would not be passed by address reference, but by value, creating instead copies of their values. In this case, the output of the program would have been the values of x, y, and z without being modified, open parenthesis, that is, 1, 3, and 7, close parenthesis. Efficiency considerations and const references. Calling a function with parameters taken by value causes copies of the values to be made. This is a relatively inexpensive operation for fundamental types such as int, but if the parameter is of a large compound type, it may result in significant overhead. For example, consider the following for-line function. Line 0, 1 of 0 for string concatenate, open parenthesis, string A, comma, string B, close parenthesis. Line 0, 2 of 0 for open curly brace. Line 0, 3 of 0 for return A plus B, semicolon. Line 0, 4 of 0 for close curly brace. This function takes two strings as parameters, open parenthesis, by value, close parenthesis, comma, and returns the result of concatenating them. By passing the arguments by value, the function forces A and B to be copies of the arguments passed to the function when it is called. And if these are long strings, it may mean copying large quantities of data just for the function call. But this copy operation can be avoided altogether if both parameters are passed through address references, as shown in these 4 lines colon. Line 0, 1 of 0 for string concatenate, open parenthesis, string ampersand, A, comma, string ampersand, B, close parenthesis. Line 0, 2 of 0 for open curly brace. Line 0, 3 of 0 for return A plus B, semicolon. Line 0, 4 of 0 for close curly brace. Unlike regular arguments, arguments by address reference do not require an extra copy within the function. The function operates directly on addresses of the strings passed as arguments, and, at most, it might mean the transfer of certain pointers to the function. In this regard, the version of concatenate taking address references is more efficient than the version taking values, since the function's initialization logic does not need to copy potentially large, cumbersome strings. The concatenation operation accumulates the result directly from the two source variables without making any extra temporary copies. On the flip side, functions with parameters referenced by address are generally perceived as functions that modify the actual arguments passed, wherever they may be in the computer's memory, because that is why reference parameters are actually used. Our little example does not actually modify either of the address references A or B, but functions could be written that could do so, and that might sometimes be undesirable, since referenced locations of the associated variables are not going to move. It is possible to protect those locations from modification by the function. This can be done by qualifying the parameters as constant comma, as in these 4 lines colon. Line 0, 1 of 0 for string concatenate, open parenthesis, const string ampersand, A, comma, const string ampersand, B, close parenthesis. Line 0, 2 of 0 for open curly brace. Line 0, 3 of 0 for return A plus B, semicolon. Line 0, 4 of 0 for close curly brace. By qualifying them as const, the function is forbidden to modify the values of A or B, comma, but can actually access their values as references, open parenthesis, aliases of the arguments, close parenthesis, comma, without having to make actual copies of the strings. Therefore, const references provide functionality similar to passing arguments by value, but with an increased efficiency for parameters of large types. That is why they are extremely popular in C++ for arguments of compound types. Note, though, that for most fundamental types, there is no noticeable difference in efficiency, and in some cases, const references may even be less efficient. Inline functions. Calling a function generally causes a certain overhead, open parenthesis, stacking arguments, jumps, etc., point, close parenthesis, comma, and thus for very short functions, it may be more efficient to simply insert the code of the function where it is called, instead of performing the process of formally calling a function. Preceding a function declaration with the inline specifier informs the compiler that inline expansion is preferred over the usual function call mechanism for a specific function. This does not change the behavior of a function at all, but is merely used to suggest to the compiler that the code generated by the function body ought to be inserted at each point where the function is called, instead of being invoked with a regular function call. For example, the concatenate function above may be declared inline, as in these 4 lines colon. Line 0, 1 of 0 for inline string concatenate, open parenthesis, const string ampersand, A, comma, const string ampersand, B, close parenthesis. Line 02 of 04, open curly brace. Line 03 of 04, return A plus B, semicolon. Line 04 of 04, close curly brace. This informs the compiler that when concatenate is called, the program prefers the function to be expanded inline, instead of performing a regular call. Inline is only specified in the function declaration, not when it is called. Note that most compilers already optimize code to generate inline functions when they see an opportunity to improve efficiency, even if not explicitly marked with the inline specifier. Therefore, the specifier merely indicates to the compiler that inline is preferred for this function, although the compiler is free to not inline it and optimize otherwise. In C++, optimization is a task delegated to the compiler, which is free to generate any code, as long as the resulting behavior is the one specified by the code. Default values and parameters. In C++, functions can also have optional parameters, for which no arguments are required in the call, in such a way that, for example, a function with 3 parameters may be called with only 2. For this, the function must include a default value for its last parameter, which is used by the function when called with fewer arguments. For example, consider this 17-line example : line 01 of 17 / default values in functions. Line 02 of 17, $, include left angle bracket, iostream right angle bracket. Line 03 of 17, using namespace std, semicolon. Line 04 of 17. Line 05 of 17, int divide, open parenthesis, int a, comma, int b equals 2, close parenthesis. Line 06 of 17, open curly brace. Line 07 of 17, int r, semicolon. Line 08 of 17, r equals a / b, semicolon. Line 09 of 17, return, open parenthesis, r, close parenthesis, semicolon. Line 10 of 17, close curly brace. Line 11 of 17. Line 12 of 17, int main, open parenthesis, close parenthesis. Line 13 of 17, open curly brace. Line 14 of 17, cout, double left arrow, divide, open parenthesis, 12, close parenthesis, double left arrow, single quote, new line, single quote, semicolon. Line 15 of 17, cout, double left arrow, divide, open parenthesis, 20, 4, close parenthesis, double left arrow, single quote, new line, single quote, semicolon. Line 16 of 17, return 0, semicolon. Line 17 of 17, close curly brace. When this code is executed, the following output results. 6.5. In this example, there are 2 calls to function divide. In the first one, divide, open parenthesis, 12, close parenthesis. The call only passes 1 argument to the function, even though the function has 2 parameters. In this case, the function assumes the second parameter to be 2, open parenthesis. Notice the function definition, which declares its second parameter as int a equals 2, close parenthesis. Therefore, the result is 6. In the second call, divide, open parenthesis, 20, 4, close parenthesis. The call passes 2 arguments to the function. Therefore, the default value for b, open parenthesis, int b equals 2, close parenthesis, is ignored, and b takes the value passed as argument, that is 4, yielding a result of 5. Declaring functions. In C++, identifiers cannot be used in any expressions until after the compiler has seen a declaration for them. For example, some variable x cannot be used before being declared with a statement, such as int x, semicolon. The same applies to functions. Functions cannot be called before they are declared. That is why, in all the previous examples, all of our new functions were always defined before main, open parenthesis, close parenthesis, comma, which is the function from which all other functions are called. If main were defined before the other functions, this would break the rule that functions shall be declared before being used, and thus the resulting code would not compile. Sometimes this restriction makes for a cumbersome or confusing arrangement of functions within a large, complex program. It is generally desirable to organize the location of functions into positions that correspond with the actual sequence of execution, or into alphabetical order by name, so that they can be found by human programmers who may need to read the code later on. This restriction can be overcome through use of a mechanism known as a double quote function prototype double quote. The prototype of a function can be declared without actually defining the function completely, giving just enough details to allow the types involved in a function call to be known to the compiler, so it can allocate named memory for it in advance, and also for any data that it will need in order to accept and deliver the appropriate parameters. Naturally, the function must eventually be completely defined somewhere else, probably later in the code. But at least, once declared like this, the compiler will not complain when it is asked to prepare to invoke it by name, and to pass arguments into it and out of it. The prototype gives the compiler enough information to trust that those details can be filled in later. Of course, the declaration of a function prototype must include all types involved, open parenthesis, the return type and the type or types of its arguments, close parenthesis, comma, using the same syntax as used in the definition of the function, but replacing the body of the function, open parenthesis, the block of statements, close parenthesis, with just a single, ending semicolon. This shorthand tells the compiler that it has found a prototype declaration and not the actual definition of the function. In a function prototype, the parameter list does not need to include the parameter names, but only their types. Parameter names can nevertheless be specified, but they are optional, and do not need to necessarily match those in the function definition. For example, a function called protofunction expecting two integer parameters can be declared with either of these statements. Prototype 1 of 2, in protofunction, open parenthesis, in first comma, in second, close parenthesis, semicolon. Prototype 2 of 2, in protofunction, open parenthesis, int comma, int, close parenthesis, semicolon. Although names like those shown in the first example above are not required, experience has shown that including a name for each parameter usually improves legibility of the declaration. Here is a 30-line program showing use of function prototypes. Line 0, 1 of 30, / declaring function prototypes. Line 0, 2 of 30, $, include left angle bracket, IOStream right angle bracket. Line 0, 3 of 30, using namespace std, semicolon. Line 0, 4 of 30. Line 0, 5 of 30, / prototypes for two functions we intend to write and use. Line 0, 6 of 30, void odd, open parenthesis, index, close parenthesis, semicolon. Line 0, 7 of 30, void even, open parenthesis, index, close parenthesis, semicolon. Line 0, 8 of 30. Line 0, 9 of 30, int main, open parenthesis, close parenthesis. Line 10 of 30, open curly brace. Line 11 of 30, int I, semicolon. Line 12 of 30, 2, open curly brace. Line 13 of 30, cout, double left arrow, double quote, please, enter number, open parenthesis 0 to exit, close parenthesis, colon double quote, semicolon. Line 14 of 30, cin, double right arrow I, semicolon. Line 15 of 30, odd, open parenthesis, I, close parenthesis, semicolon. Line 16 of 30, close curly brace, while, open parenthesis, I exclamation, equals 0, close parenthesis, semicolon. Line 17 of 30, return 0, semicolon. Line 18 of 30, close curly brace. Line 19 of 30. Line 20 of 30, void odd, open parenthesis, index, close parenthesis. Line 21 of 30, open curly brace. Line 22 of 30, if, open parenthesis, x%2, close parenthesis, exclamation, equals 0, close parenthesis, cout, double left arrow, double quote, it is odd, new line, double quote, semicolon. Line 23 of 30, else even, open parenthesis, x, close parenthesis, semicolon. Line 24 of 30, close curly brace. Line 25 of 30. Line 26 of 30, void even, open parenthesis, index, close parenthesis. Line 27 of 30, open curly brace. Line 28 of 30, if, open parenthesis, x%2, close parenthesis, equals 0, close parenthesis, cout, double left arrow, double quote, it is even, new line, double quote, semicolon. Line 29 of 30, else odd, open parenthesis, x, close parenthesis, semicolon. Line 30 of 30, close curly brace. Here is some sample output generated by an operator running this program. Please, enter number, open parenthesis 0 to exit, close parenthesis, :9. It is odd. Please, enter number, open parenthesis 0 to exit, close parenthesis, :6. It is even. Please enter number, open parenthesis 0 to exit, close parenthesis, colon 1030. It is even. Please enter number, open parenthesis 0 to exit, close parenthesis, colon 0. It is even. This example is indeed not an example of efficiency. You can probably write yourself a version of this program with half the lines of code. Nevertheless, note that in this program, our double quote, main double quote, function can now be found before the functions double quote, even double quote, and double quote, odd double quote, are completely defined, resulting in a more natural arrangement of the source code. This example illustrates how functions can be declared early in a program so that they can be invoked before the compiler finds their complete definitions. The following two lines. Line 01 of 02 void odd, open parenthesis, int a. Line 02 of 02 void even, open parenthesis, int a. Declare the prototypes of the two corresponding functions. They already reveal all that is necessary to call them, their name, the types of their argument or arguments, and their return type, open parenthesis, void in this case, close parenthesis. With these prototype declarations in place, they can be called, before they are entirely defined, allowing for example, to place the function from, where they are called, open parenthesis, main, close parenthesis, before the actual definition of these functions. But declaring functions before being defined is not only useful to reorganize the order of functions within the code. In some cases, such as in this particular case, at least one of the declarations is required, because odd and even are mutually called, semicolon, there is a call to even in odd and a call to odd in even. And, therefore, there is no way to structure the code so that odd is defined before even, and even before odd. Recursion. Recursion is the property that functions use when they have to be called by themselves. For humans, this is a strange and unnatural concept, but it is easy for computers, and it is useful for some tasks, such as sorting elements, or calculating the factorial of numbers. For example, in order to obtain the factorial of a number, open parenthesis, an exclamation, close parenthesis, the mathematical formula would be n exclamation equals n asterisk, open parenthesis, n dash, 1, close parenthesis, asterisk, open parenthesis, n dash, 2, close parenthesis, asterisk, open parenthesis, n dash, 3, close parenthesis, point, asterisk, 1. More concretely, 5 exclamation, open parenthesis, factorial of 5, close parenthesis, would be 5 exclamation equals 5 asterisk, 4 asterisk, 3 asterisk, 2 asterisk, 1 equals 120. A recursive function to calculate this in C++ could be implemented with the following 18 lines of code. Line 01 of 18 / factorial calculator. Line 02 of 18, $, include left angle bracket, iostream right angle bracket. Line 03 of 18, using namespace std semicolon. Line 04 of 18. Line 05 of 18, long factorial, open parenthesis, long x, close parenthesis. Line 06 of 18, open curly brace. Line 07 of 18, if, open parenthesis, x right angle bracket, 1, close parenthesis. Line 08 of 18, return, open parenthesis, x asterisk, factorial, open parenthesis, x dash, 1, close parenthesis, semicolon. Line 09 of 18, else. Line 10 of 18, return 1, semicolon. Line 11 of 18, close curly brace. Line 12 of 18. Line 13 of 18, int main, open parenthesis, close parenthesis. Line 14 of 18, open curly brace. Line 15 of 18, long number equals 9, semicolon. Line 16 of 18, cout, double left arrow, number, double left arrow, double quote, exclamation, equals double quote, double left arrow, factorial, open parenthesis, number, close parenthesis, semicolon. Line 17 of 18, return 0, semicolon. Line 18 of 18, close curly brace. Running this program will yield the following output. 9 equals 362,880. Notice how in function factorial we included a call to factorial itself, but only if the argument passed was greater than 1. Furthermore, within the loop that continues to invoke factorial, we ensure that the argument is repeatedly decremented, so that it will eventually be less than 1. That test for argument greater than 1 provides important protection against an infinite runaway loop. Without it, the function could fall into an infinite recursive loop, in which it would continue invoking itself and multiplying forever until something fails somewhere, open parenthesis, probably provoking a stack overflow at some point during runtime, close parenthesis.